What if everything we think we know about the universe is just the surface of something far stranger? Picture standing at the edge of an endless ocean, staring into its depths only to realize the water isn't just dark and empty. Beneath the waves there are currents, layers, entire worlds we can't see from the shore. That's the unsettling truth behind our cosmos. The universe might be hiding secrets so profound they rewrite the rules of reality itself. And today, we're diving into 30 of the most mind-bending theories that suggest our reality isn't what it seems, from hidden dimensions folded like origami around us, to parallel universes brushing against our own like ghosts in the cosmic dark. Some of these ideas sound like science fiction, but they're rooted in cutting-edge physics, mathematics, and observations that leave even the brightest scientists questioning everything. Imagine a universe where time isn't linear but a tangled web of possibilities, or one where dark matter isn't just invisible, it's an entire shadow reality vibrating just out of reach. These aren't just wild guesses, they're serious attempts to explain the gaps in our understanding, the anomalies that keep astrophysicists awake at night. Like why galaxies spin faster than they should, or why the cosmos seems to be expanding at speeds that defy logic. So why does any of this matter? Because every time humanity peels back a layer of the universe, we uncover something that reshapes our place in it. Whether it's realizing Earth isn't the center of the solar system, or discovering that space itself is stretching like elastic, these revelations don't just change textbooks, they change how we see ourselves. And right now, we're on the brink of another seismic shift. The theories we're about to explore aren't just curiosities, they're clues to a puzzle we're only beginning to solve. So if you've ever looked up at the stars and wondered what's really out there, stick around. This journey isn't just about the universe's hidden layers. It's about discovering what they mean for all of us. One of the most startling ideas in modern physics suggests that everything we experience, every galaxy, every planet, even your own hands, might be nothing more than an incredibly convincing illusion. This is the holographic principle, the theory that our three-dimensional reality could actually be a projection from a two-dimensional surface at the far edges of the universe. Think of it like a cosmic movie screen, where the flat surface contains all the information needed to construct the rich, multidimensional world we perceive. The idea first gained traction in the 1990s when physicist Leonard Susskind and others realized that the mathematics of black holes pointed to something bizarre. The information swallowed by these cosmic monsters wasn't lost forever but seemed to be encoded on their surfaces like data etched onto a celestial hard drive. This led to the AD-S/CFT correspondence, a groundbreaking framework that mathematically links theories of gravity in higher dimensions to quantum theories operating on a lower dimensional boundary. In simpler terms, it suggests that the universe might work like a hologram, where a two-dimensional surface holds the blueprint for everything we see and feel in 3 dimensions. If true, it would mean space-time isn't fundamental, it's emergent, a side effect of deeper quantum interactions playing out on the cosmic fringe. But how could this possibly be real? One clue comes from black holes. When matter falls into one, physics tells us the information it carries can't just vanish. Instead, theorists propose it gets smeared across the event horizon, the point of no return, like ink spreading on a page. The holographic principle takes this further, suggesting all the information in the universe might be similarly stored on its outer boundary. It's as if the universe itself is a vast, intricate projection, and we're just shadows dancing on its walls. Scientists are still untangling what this means for our understanding of reality. If space and time are just illusions, then concepts like distance and duration might not be as fixed as they seem. The idea also raises wild possibilities. Could we one day decode the universe's hidden data? Could we manipulate the projection to reveal layers of reality we've never seen? For now, these questions remain unanswered, but the holographic principle forces us to confront a humbling truth. The universe might be far stranger and far more interconnected than we ever imagined. Just when you thought the holographic principle couldn't make reality any stranger, another theory throws the cosmic rulebook out the window entirely. Imagine our universe isn't alone, not even close. Instead, it's just one bubble in an endless froth of universes, each with its own laws of physics, its own history, maybe even its own version of you. This is the Level 1 multiverse, a consequence of cosmic inflation, the theory that our early universe expanded faster than light in a fraction of a second after the Big Bang. Proposed by physicist Alan Guth in the 1980s, inflation doesn't just explain why the cosmos looks so smooth and uniform, it suggests the expansion might never have stopped. Some regions of space could still be inflating right now, stretching into entirely new universes like bubbles forming in an infinite cosmic kettle. Here's where it gets wild. Quantum fluctuations, tiny, random wobbles in energy, could trigger these bubbles to pinch off and become their own self-contained realities. Picture blowing soap bubbles on a windy day. Some pop immediately, others drift away untouched. Universes might form the same way, with some lasting milliseconds and others enduring for trillions of years. And because each one cools differently, the fundamental forces inside them could vary. One might have gravity 100 times stronger than ours, making stars burn out in days. Another could have no electromagnetism at all, leaving it dark and lifeless. The implications are staggering. If inflation is eternal, there could be an infinite number of universes out there, each a unique experiment in physics. But how could we ever prove something so extraordinary? For now, the multiverse remains a prediction of mathematics, not direct observation. Some scientists hunt for faint imprints in the cosmic microwave background, the afterglow of the Big Bang that might reveal collisions between our universe and a neighboring bubble. Others study the distribution of galaxies, looking for anomalies that could hint at a larger cosmic structure. And while critics argue the multiverse is untestable metaphysics, supporters counter that it's no different from early theories about atoms or black holes, ideas once deemed speculative now confirmed. The real mind bender: if the multiverse exists, every possible outcome might be happening somewhere. A version of you just scratched their nose, another is reading these words in a universe where gravity pushes instead of pulls. It's a dizzying thought, but it raises profound questions. Are we just one thread in an infinite tapestry? And if so, what does that say about the nature of existence itself? String theory takes the multiverse concept to even more dizzying heights. While Level 1 imagined infinite bubble universes spawned by cosmic inflation, Level 2 proposes something even more radical. That other universes might not just have different histories, but entirely different laws of physics. Imagine a cosmic library where every book isn't just a variation of the same story, but written in different languages with different alphabets, some so alien we couldn't even turn their pages. That's the landscape of string theory, where tiny, vibrating strands of energy could give rise to universes with fundamentally different rules. At the heart of this idea is the notion of extra dimensions. String theory suggests there might be up to 10 or 11 dimensions curled up so small we'll never perceive them. But here's the twist: the way those dimensions fold and vibrate could determine everything from gravity's strength to the mass of electrons. Physicist Brian Greene likens it to a cosmic switchboard. Tweak one setting and you get a universe where atoms can't form. Tweak another and stars might never ignite. In this vast landscape of possibilities, our universe's delicate balance, where gravity is weak enough for galaxies to form but strong enough to hold them together, might not be special. It's just one combination in a near-infinite array. This leads to the anthropic principle, the philosophical razor that asks, why does our universe seem so finely tuned for life? The answer might be startlingly simple, because if it weren't, we wouldn't be here to ask the question. In a multiverse where every possible set of physical constants exists, conscious observers will only find themselves in the rare universes compatible with their existence. It's like waking up in a room with the thermostat perfectly set for your comfort. You might think someone adjusted it just for you, but the truth could be that there are a million other rooms, some freezing, others boiling, and you just happen to open the right door. Critics argue this sounds like a cop-out, a way to explain fine-tuning without invoking deeper laws. But supporters point to string theory's mathematical consistency as evidence. The theory doesn't just allow for multiple universes, it practically demands them. Simulations show that even slight changes to our universe's constants often lead to sterile, lifeless voids. Yet in a multiverse, those failed experiments are balanced by the rare gems like ours. The stakes couldn't be higher. If true, this reshapes not just cosmology but philosophy. Are the laws of physics inevitable or just a roll of the cosmic dice? Could other universes harbor forms of life we can't even conceive? For now, these questions hover at the edge of science, but the mere possibility forces us to rethink our place in the cosmic order. Far from being the center of existence, we might be one fragile thread in a tapestry so vast it redefines the word universe itself. If the idea of bubble universes or cosmic strings seemed strange, wait until you hear what quantum mechanics has to say about reality. There's a version of the multiverse so bizarre it suggests every choice you've ever made, and every choice you didn't spawns an entirely new universe. This is the many worlds interpretation, a radical take on quantum physics that turns probability into parallel timelines. Forget alternate universes with different laws of physics. This theory proposes near-identical copies of our world splitting apart every nanosecond, each one hosting a different outcome of every quantum event. The story begins in the 1950s with physicist Hugh Everett, a graduate student who dared to ask, what if quantum superposition, the idea that particles exist in multiple states until observed, isn't just about particles? What if it applies to the entire universe? Everett's math suggested that when a quantum event occurs, like an electron choosing a path or a radioactive atom decaying, the universe doesn't pick one outcome. Instead, it branches into multiple versions, each bearing witness to a different result. Picture standing at a fork in the road where both paths are taken not by you, but by alternate versions of you, splitting like reflections in a hall of mirrors. This reframes one of quantum mechanics' most famous thought experiments, Schrödinger's cat. In the original version, a cat in a box is both alive and dead until someone opens it and collapses the probabilities into a single reality. But Many Worlds flips this on its head. There's no collapse, just two universes, one with a relieved purring cat, another with, well, a very different outcome. Every quantum decision, no matter how small, becomes a branching point. Did you turn left at the traffic light this morning? Somewhere, another you turned right. Did you hesitate before clicking on this video? In another reality, you didn't. The implications are staggering. If Many Worlds is correct, there's a universe where Napoleon won at Waterloo, where dinosaurs never went extinct, where you pursued that career you once dreamed about. But here's the twist, these branches aren't science fiction. They're mathematical necessities baked into the equations of quantum theory. The catch: we can't access them. Once a universe splits, it's forever out of reach, like a train speeding down a parallel track you can see but never board. Critics argue this is philosophy disguised as physics, an elegant solution that can't be tested. Supporters counter that it's the simplest explanation for quantum weirdness, removing the need for mysterious observers to collapse probabilities. Some even hunt for indirect evidence, like quantum particles that seem to remember paths they didn't take. Whether proven or not, Many Worlds forces us to confront a humbling truth. The universe might not just be stranger than we imagine, but stranger than we can imagine. Every moment could be a doorway to infinite versions of reality, each as real as the one you're experiencing right now. While the many worlds interpretation suggests countless branching realities based on quantum choices, Max Tegmark takes the multiverse concept to its ultimate extreme. His mathematical universe hypothesis proposes that every possible mathematical structure isn't just a description of reality, it is reality. Think of numbers not as tools we invented to measure the world, but as the very fabric of existence itself. In this breathtaking vision, universes aren't limited by physical laws or even logic as we know them. If a structure can be described mathematically, it exists somewhere in the grand scheme of things, from orderly cosmos like ours to chaotic realms where time flows backward or shapes have 12 dimensions. Tegmark's framework divides the multiverse into 4 levels, each more expansive than the last. Level 1, as we've seen, includes bubble universes born from eternal inflation. Level 2 introduces universes with different physical constants. Level 3 covers the quantum branching of many worlds, but Level 4 demolishes all boundaries. Here, even the most outlandish mathematical constructs say, a universe where pi equals 3, or where gravity behaves like a swirling symphony, must exist simply because the equations allow it. It's not that the universe is described by math, it is math. We're just one particular self-aware substructure within an infinite tapestry of numerical possibility. This radical idea stems from a simple but profound observation. Mathematics has an uncanny ability to predict physical phenomena we haven't even discovered yet. Equations written centuries ago correctly described planets we couldn't see and forces we couldn't measure. Tegmark argues this isn't coincidence, it's evidence that math isn't merely a human invention, but the underlying language of existence. To illustrate, imagine a spreadsheet so vast, every cell contains an entire universe. Some sheets look like ours with stars and atoms. Others resemble abstract art, filled with geometric patterns that think and feel. The spreadsheet isn't running these worlds, it is these worlds, and every cell is equally real. Critics question whether this hypothesis is science or metaphysics. How could we ever test the existence of a universe based on entirely alien mathematics? Tegmark suggests looking for anomalies in our own cosmos, places where the rules seem to break down, hinting at deeper layers of mathematical structure. Others propose that consciousness itself might be a key, since self-aware observers like us can only emerge in certain mathematical substructures capable of supporting complexity. The implications are staggering. If Tegmark is right, reality isn't just stranger than we imagine, it's stranger than we can imagine, limited only by the boundaries of logic itself. There could be universes where light travels in spirals, where emotions have physical shapes, or where the concept of nothingness is impossible. This isn't just about alternate versions of Earth, it's about entirely alternate frameworks of existence. The mathematical universe hypothesis doesn't just expand our idea of reality. It dissolves the line between physics and philosophy, leaving us with a humbling truth. We may not live in the universe, but in one tiny corner of an infinite mathematical library, where every equation on every page is its own vivid, breathing world. What if our universe isn't floating in empty space at all, but stretched like a sheet in a cosmic laundry line, surrounded by unseen dimensions we can't touch or see? This is the essence of brain cosmology, a theory that reimagines reality as a membrane or brain, drifting through a higher dimensional realm called the bulk. Imagine a loaf of sliced bread where each slice is its own universe, hovering inches apart but forever separated by an unfathomable gap. Our entire cosmos, every star, every planet, could be confined to just one of those slices, while parallel worlds vibrate right beside us, invisible yet tantalizingly close. The idea gained traction in the 1990s with physicists like Lisa Randall and Raman Sundram, who proposed that gravity, the force that holds galaxies together, might actually be leaking into our brain from higher dimensions. Picture a water droplet soaking through a paper towel. Gravity could behave similarly, seeping into our universe from the bulk and explaining why it feels so weak compared to other fundamental forces. Randall's work suggests these extra dimensions aren't the tiny, curled-up strings of string theory, but vast expanses, potentially large enough to hide entire shadow universes. One of the most dramatic versions of this theory is the ekpyrotic model, which dares to rewrite the Big Bang itself. Instead of a singular explosion, it proposes our universe began when two brains floating like cosmic sheets in higher dimensional space collided. The energy of that crash could have ignited everything we see today, like striking a match against the walls of reality. Even more intriguing, the model suggests these collisions might be cyclical, meaning universes could bounce into existence over and over forever. But how do we test something so abstract? Enter the Large Hadron Collider. Scientists have hunted for clues of extra dimensions by smashing particles together at nearly the speed of light, hoping to catch glimpses of energy vanishing into higher realms. In 2010, rumors swirled that the LHC might have detected microscopic black holes, a potential sign of gravity leaking into other dimensions. Though those findings were later debunked, the search continues, with some theorists suggesting that dark matter itself might be ordinary matter trapped on a neighboring brain, forever out of reach yet gravitationally tugging at ours. Brain cosmology doesn't just challenge our understanding of space, it redefines what a universe even is. If true, the night sky isn't just a window to distant stars, but a flickering projection from a realm we're only beginning to fathom. And somewhere beyond our perception, other brains might ripple like sails in an unseen wind, carrying realities so alien they make the multiverse look tame. Picture a civilization so advanced their technology could recreate entire universes in perfect detail, down to the last quark in your fingernail. Now ask yourself, how would you know if you weren't just a line of code in their cosmic computer? This is the simulation hypothesis, the theory that our reality might not be the base layer of existence, but an artificial construct running on some unfathomable hardware. Philosopher Nick Bostrom laid the groundwork in 2003 with a chilling trilemma. At least one of these statements must be true. 1. Almost all civilizations at our level go extinct before developing simulation technology. 2. If they survive, they almost never choose to run ancestor simulations, high-fidelity recreations of their past. Or 3. We're almost certainly living in a simulation right now. The logic is deceptively simple. If future civilizations can simulate conscious minds, and they have even a modest interest in running such experiments, the number of simulated beings would dwarf the number of real ones. Statistically, the odds tilt overwhelmingly toward us being among the simulations. Think of it like video games. Early home computers could barely render a few pixels, yet today's games craft entire worlds with physics, weather, and AI that react to players. Extrapolate that progress 1,000 or 1,000,000 years, and creating a universe indistinguishable from real life starts to seem inevitable. Tech billionaire Elon Musk famously argued we're almost certainly inside such a simulation, stating the alternative, that humanity will never reach that level of technological maturity, would defy the exponential curve of innovation. But Bostrom's trilemma leaves room for skepticism. Maybe simulating consciousness is fundamentally impossible, no matter how advanced the tech. Or perhaps ethical concerns prevent post-human civilizations from creating sentient digital beings. Yet even these objections have counter-arguments. If consciousness arises from information processing, as many neuroscientists believe, then replicating it might just be a matter of computational power. And ethics, human history suggests we rarely resist using new technology, even when we should. The most haunting evidence might come from quantum mechanics itself. Why do particles exist in fuzzy superpositions until observed? Some theorists propose it's an optimization trick. The simulation only renders what's being measured to save processing power, like a video game loading graphics as the player moves. Even glitches in the cosmic code have been suggested, like the infamous Mandela effect, where large groups misremember events identically. Could these be patches or updates in the simulation's programming? Yet for all its intrigue, the hypothesis faces a glaring problem. If the simulation is flawless by design, how could we ever prove it's not real? Some physicists propose hunting for pixelation in the fabric of space-time at unimaginably small scales. Others suggest looking for mathematical constraints in physical constants, like rounding errors in the universe's source code. But until then, the simulation hypothesis remains a mirror held up to our own technological ambitions, one that reflects back an unsettling question. If we're ever capable of creating such simulations, how will we treat the conscious beings inside them? And if we're already in one, what does that say about the nature of reality or the purpose of our existence? The answers might redefine not just science, but what it means to be alive. What if time isn't a river flowing relentlessly forward, but a frozen landscape where every moment exists eternally? Physicist Julian Barber's radical theory throws out the clock entirely, proposing that the universe isn't moving through time at all. It's a vast, static sculpture of nows, and what we perceive as change is just an illusion woven by our limited perspective. Imagine a flipbook where every page shows a different frame of an animation. Flipping through it creates the illusion of motion, but each page exists independently, unchanging. Barber suggests reality works the same way. The universe isn't evolving, it simply is, with every possible configuration stacked like pages in an infinite cosmic book. This idea, called timeless physics, challenges Einstein's view of time as a flexible dimension in space-time. Instead, Barber's math treats time as an emergent property, something that arises from relationships between objects rather than an intrinsic force. Picture a movie played one frame at a time. The story only makes sense because our brains stitch the frames together. Similarly, Barber argues that sequences of quantum states create the sensation of time passing, even though all those states exist simultaneously in a timeless whole. One striking consequence: the past and future might not be out there waiting to happen, they're already here, just not from our vantage point. Think of a mountain range where each peak represents a moment in what we call history. From the ground, you only see one peak at a time, but a bird's eye view reveals the entire range at once. In Barber's universe, the Big Bang isn't an event that happened 13.8 billion years ago. It's a permanent feature of the landscape, as real and present as the phone in your hand. Critics ask, if time isn't fundamental, why does it feel so undeniably real? Supporters point to quantum mechanics, where particles seem to know about future measurements in ways that defy classical time. Experiments like the delayed choice quantum eraser suggest that observations made now can retroactively alter a particle's past behavior, as if time's arrow is more suggestion than law. Even entropy, the usual marker of time's direction, might just be a statistical quirk in how we sample the timeless whole. The implications are dizzying. Free will, cause and effect, even aging could be side effects of how consciousness navigates this frozen multiverse of nows. Barber's vision doesn't just reshape physics, it reframes existence itself. If he's right, the universe isn't a story unfolding in time. It's a gallery of every possible moment hanging side by side forever, and we're not travelers moving through it. We're the gallery experiencing itself one frame at a time. Imagine a universe where the Big Bang wasn't a one-time event, but just the first spark in an endless cosmic fireworks show, where new universes inflate into existence constantly, like bubbles in a never-ending champagne pour. This is eternal inflation, a theory that reshapes our understanding of the cosmos by suggesting that the rapid expansion of space didn't just happen once, 13.8 billion years ago, but is still happening right now in regions far beyond our observable horizon. Physicist Andre Lin's groundbreaking work on chaotic inflation takes this further, proposing that the primordial energy field driving this expansion isn't uniform, but a turbulent sea of quantum fluctuations. Picture a pot of water boiling violently. Some bubbles grow and pop near the surface, while others merge or drift away. In Lin's model, each of these bubbles becomes its own self-contained universe with its own unique physics, born from random ripples in the fabric of space-time. The implications are staggering. Our entire cosmos might be just one bubble in an infinite foam of universes, each with its own version of reality. Some could have stronger gravity, making stars burn out in seconds. Others might lack electromagnetism, leaving them dark and frozen. And because inflation never truly stops, only pausing locally to form bubble universes like ours, the multiverse becomes fractal, branching endlessly into the future. Lin's chaotic inflation suggests there's no single, correct set of initial conditions for the Big Bang. Instead, every possible configuration of physics gets tried somewhere in this cosmic lottery, with universes sprouting from quantum chaos like wildflowers in a meadow. But how does this fit with the Big Bang we know? Think of it like resetting the cosmic clock. The moment inflation ends inside a bubble, when that primordial energy field finally decays, releases a burst of heat and particles, creating what we perceive as the Big Bang. But outside our bubble, inflation rages on, spawning new universes in an unending cascade. This means the Big Bang wasn't the absolute beginning, it was just the start of our local neighborhood. Elsewhere, the process repeats infinitely with no center and no edge, like a hall of mirrors reflecting forever. Evidence for eternal inflation is indirect but compelling. Tiny temperature variations in the cosmic microwave background, the afterglow of our own Big Bang, hint at quantum fluctuations stretched across the sky by inflation. Some models predict that colliding bubble universes might leave bruises in this radiation, though none have been found yet. Others suggest that the universe's flat geometry, where parallel lines never meet, is a natural byproduct of eternal inflation's relentless stretching. The theory also solves a profound puzzle. Why does our universe seem so finely tuned for life? In an infinite multiverse, every possible set of physical constants exists somewhere. Most are barren, but a rare few like ours strike the delicate balance needed for atoms, stars, and thinkers. It's not luck, it's statistics. We exist because we can't observe the countless failed experiments where life was impossible. Eternal inflation doesn't just challenge our origin story, it redefines the very nature of existence. If Lind is right, reality isn't a single narrative with a beginning and end. It's an endless library of universes, each telling its own story, forever branching into the unknown. And somewhere beyond the edge of our bubble, new chapters are being written right now in a cosmic saga without end. What if the universe isn't a one-time explosion but a cosmic accordion, expanding and contracting in an endless, rhythmic dance? This is the heart of cyclic cosmology, a theory that replaces the traditional Big Bang with a universe that breathes, collapsing and reborn over and over, each cycle lasting trillions of years. Physicist Paul Steinhardt's vision isn't just about repetition. It's a radical reimagining of dark energy, the mysterious force accelerating the universe's expansion as the very engine of cosmic rebirth. Picture a universe where the end isn't cold and dark, but the prelude to another beginning. In Steinhardt's model, dark energy, often thought of as a relentless force tearing space apart, plays a surprising dual role. Initially, it drives galaxies away from each other at ever-increasing speeds, stretching the fabric of reality until matter is spread so thin, it becomes virtually invisible. But here's the twist: as dark energy's properties evolve, it doesn't just keep pushing. At a critical point, it flips the script, becoming an attractive force that reverses the expansion. Space itself begins to contract, pulling galaxies back together in a slow-motion collapse. matter heats up, stars melt into plasma, and eventually the entire universe crunches down to an unimaginably hot, dense state, a seed for the next Big Bang. This cyclical process solves some of cosmology's biggest puzzles. For one, it dodges the need for a singularity, a point of infinite density where physics breaks down by replacing it with a smooth bounce. Think of a rubber band snapping back after being stretched too far. The universe doesn't vanish into a black hole of its own making. It rebounds refreshed and ready for a new cycle. It also explains why our universe appears so finely tuned for complexity. Each cycle isn't a perfect reset. Quantum fluctuations from the previous iteration leave subtle imprints like cosmic breadcrumbs, steering the next universe toward conditions that allow galaxies, stars, and life to form. Over countless cycles, the universe learns, in a sense, how to build itself better. Critics argue that cyclic cosmology is hard to test. How do you find evidence of a universe that existed before time as we know it? Supporters point to the cosmic microwave background, the faint glow of the Big Bang, for possible clues. If a previous cycle left wrinkles in space-time, they might faintly echo in this radiation like shadows of a forgotten age. Others suggest that dark energy's behavior holds the key. If its strength changes over time, as cyclic models predict, future telescopes could detect shifts in how fast supernovae are racing away from us. The most profound implication: time might be infinite, but not in the way we usually imagine. There's no true beginning or end, just an endless loop of creation and destruction, each cycle writing its own chapter in a story without a first page or final sentence. Steinhardt's universe isn't a one-act play. It's an eternal encore with dark energy as both the curtain and the director. And somewhere in this grand cosmic theater, we're not just spectators. We're fleeting characters in a saga that has no finale, only another act waiting in the wings. What if black holes aren't cosmic dead ends, but cosmic seeds scattered across the universe like hidden blueprints for the next Big Bang? This is the startling vision of Roger Penrose's conformal cyclic cosmology, a theory that rewrites the life cycle of the universe by suggesting that the end of one cosmic era becomes the raw material for the next. Unlike Steinhardt's cyclical model, which relies on dark energy's ebb and flow, Penrose's idea hinges on a process so subtle it's almost poetic: the fading of all matter into pure energy, and the silent transformation of that energy into the spark of a new beginning. At the heart of this theory is conformal rescaling, a mathematical trick that lets physicists compare vastly different scales by stretching or shrinking the fabric of space-time without altering its fundamental shape. Imagine taking a black and white photo of a mountain range and enlarging it until the grains of silver in the film become visible. The details change, but the underlying geometry stays the same. Penrose applies this concept to the universe itself, proposing that as one eon, his term for a cosmic cycle, dies, its black holes evaporate via Hawking radiation, leaving behind a universe filled with nothing but massless particles like photons. At this point, space-time becomes smooth and featureless, devoid of any sense of scale. A single photon could span the entire cosmos, or the cosmos could shrink to the size of a photon. The physics remains identical. This symmetry is the key to the rebirth. Penrose argues that the end state of the old eon can be mathematically rescaled to match the starting conditions of a new Big Bang. In essence, the infinite future of one universe becomes the singularity of the next, like a cosmic baton pass between runners in an endless relay. The most stunning implication: the information swallowed by black holes over trillions of years isn't lost. Instead, it's imprinted onto the fabric of the next universe through gravitational waves, ripples in space-time that might even explain mysterious patterns in the cosmic microwave background, which some researchers dub Hawking points. Critics highlight hurdles like the unproven nature of Hawking radiation or the challenge of preserving quantum coherence across eons. but Penrose's framework offers elegant solutions to deep puzzles, like why the early universe had such low entropy, a state resembling the smooth, high-entropy end of the previous cycle. If he's right, the universe isn't just cyclical, it's self-renewing, with black holes as the architects of its immortality. Their monstrous gravity, rather than destroying, becomes the hand that writes the first chapter of the next cosmic story. And somewhere in the echoes of those gravitational waves, the fingerprints of our universe might still linger, waiting to shape realities we'll never see. What if our universe wasn't born from a singularity, but from a cosmic Russian nesting doll, a black hole inside another universe, which itself sits inside an even larger black hole? This is the spine-tingling premise of the black hole universe hypothesis, where every collapsing star in a parent cosmos could seed an entirely new reality in its crushing depths. Theoretical physicist Nikodem Poplawski's work takes this even further, suggesting that the intense twisting of space-time inside a black hole, a property called torsion, might not just create a one-way ticket to oblivion, but a gateway to something far stranger, a white hole spewing out matter and energy in a fiery rebirth. Picture a black hole not as a cosmic trash compactor, but as the womb of a new universe. When matter falls in, the extreme gravitational forces don't just squash it into a point. They twist and stretch space-time like taffy, generating torsion. Poplawski's equations show this twisting could prevent the formation of a true singularity, instead rebounding the collapsing matter in a violent burst. To an outside observer, this looks like a black hole's infinite collapse, but from inside, it's a big bang. Our entire cosmos, with its galaxies and laws of physics, might simply be the interior of a black hole born in some higher dimensional reality, with every black hole in our universe potentially birthing its own pocket cosmos. The implications ripple outward. If true, this could solve the mystery of why our universe seems so finely tuned for life. Black holes naturally select for conditions that allow complexity. Too much crushing force and no structure forms, too little and matter scatters uselessly. Only in the narrow Goldilocks zone of a black hole's rebounding core could a universe like ours emerge. Even dark matter finds an explanation here. It might be the gravitational echo of matter in the parent universe, leaking through the cosmic umbilical cord connecting us to our origins. But how could we ever test such a fantastical idea? Clues might lie in the cosmic microwave background. If our universe inherited tiny imperfections from the torsion of its parent black hole, these could leave faint spiral patterns in the afterglow of the Big Bang. Others suggest looking for unusually aligned black hole spins, a possible fingerprint of inherited rotation from the larger cosmos, the most mind-bending possibility. If black holes spawn universes, then our own might be nested inside an infinite fractal of realities, each one a black hole inside a black hole, stretching backward and forward forever. This isn't just science fiction with equations. It's a dramatic reimagining of cosmic origins, where death and rebirth are woven into the fabric of reality itself. Black holes, often seen as the end of everything, might instead be the ultimate creators, dark engines of Genesis, turning collapse into creation and oblivion into a new beginning. And if Poplawski is right, somewhere beyond the event horizon we can never cross, another universe is already taking its first breath. What if the Big Bang wasn't the beginning of everything, but the universe's way of taking a deep breath and bouncing back? This is the heart of the Big Bounce theory, a radical alternative to the traditional singularity-based origin story. According to loop quantum gravity, a cutting-edge framework that merges quantum mechanics with general relativity, the universe might have no true beginning or end, just an endless cycle of contraction and expansion, like a cosmic heartbeat echoing across eternity. The key lies in how loop quantum gravity reimagines space-time itself. Unlike classical physics, which treats space as smooth and continuous, this theory proposes that reality is woven from tiny, indivisible loops. think of it as the universe's fabric being more like a mesh than a blank sheet. When these loops are stretched to their limits during a collapse, they don't just snap into a singularity. Instead, they generate a repulsive force so powerful, it reverses the collapse and triggers a rebound. Picture squeezing a spring with all your might just when it seems about to break. It pushes back with equal intensity, launching a new expansion. That's the big bounce, not a fiery explosion from nothingness, but a natural rebound from a previous universe's death throes. Pioneering physicist Abhay Ashtakar's work adds a crucial twist. His quantum corrections to Einstein's equations show that at extremely high densities like those in the final moments of a collapsing universe, gravity doesn't just pull matter inward. It flips, becoming a force that repels. This isn't science fiction. It's a mathematical inevitability in loop quantum cosmology. Ashtakar's models suggest that the Big Bang's singularity was never truly infinite, just an ultra-dense state where quantum effects took over, smoothing the transition from collapse to rebirth. The implications are profound. If the Big Bounce is real, our universe inherited more than just energy from its predecessor. Quantum fluctuations from the prior cycle could have imprinted themselves onto the newborn cosmos, seeding the galaxies and cosmic structures we see today. This might explain why the early universe was so remarkably uniform. Its initial conditions weren't random, but sculpted by the physics of the universe that came before. Even dark energy, the mysterious force accelerating our expansion, could be a relic of that rebound, a kind of cosmic recoil still vibrating through space-time. Critics argue that without observational evidence, the Big Bounce remains speculative. Supporters counter that loop quantum gravity's predictions, like the absence of a true singularity, are testable in principle. Some hunt for faint patterns in the cosmic microwave background that could carry echoes of a pre-bounce universe. Others simulate quantum collapses in supercomputers, watching for telltale signs of a rebound. The Big Bounce doesn't just rewrite cosmic history, it redefines our place in it. If the universe cycles endlessly, then every star, every planet, and every conscious being is part of a story much larger than a single expansion. We're not the first chapter, and we won't be the last. Instead, we're somewhere in the middle of an epic with no beginning and no end, a saga written in the quantum loops of space itself. The universe isn't just expanding, it's accelerating, driven by a mysterious force called dark energy. But what if this force isn't constant? What if it grows stronger over time, becoming so powerful it doesn't just stretch space but shreds it atom by atom? This is the nightmare scenario of phantom energy, a darker cousin of dark energy that doesn't merely push galaxies apart, it rips the cosmic fabric itself to pieces in an event cosmologists call the Big Rip. Phantom energy takes the known properties of dark energy and cranks them to 11. Current observations suggest dark energy behaves like a cosmological constant. Its density remains steady as the universe expands. But phantom energy defies this rule. Its density increases over time, meaning the more space grows, the more powerful this force becomes. Picture a rubber band being stretched. Normally, it resists until it snaps, but phantom energy is like a rubber band that gets stronger the farther you pull, until its grip overwhelms everything, even the bonds holding atoms together. The math behind this is as elegant as it is terrifying. If phantom energy's equation of state, a measure of its pressure relative to its density, dips just slightly below -1, it triggers a runaway effect. Space doesn't just expand faster, it accelerates exponentially, eventually overpowering gravity, electromagnetism, even the nuclear forces that glue particles together. First, galaxy clusters would be torn apart, then individual galaxies, stars would be plucked from their orbits, planets ripped from their suns. In the final moments, atomic nuclei would dissolve as space itself stretches faster than light can traverse it. The universe wouldn't just grow cold and empty, it would be disassembled, leaving behind a scattered sea of lonely particles unable to interact ever again. Critics argue that phantom energy is speculative. There's no direct evidence it exists. Yet some measurements of dark energy's equation of state hint at values uncomfortably close to the phantom threshold. Even more unsettling, the Big Rip isn't some distant abstraction. If phantom energy is real, calculations suggest the end could come in as little as 22 billion years, a blink on cosmic timescales. By comparison, Earth's oceans will boil away in a mere billion years as the sun grows hotter. The rip would erase all traces of our universe's history long before heat death or black hole decay could take their toll. But here's the twist: phantom energy might not be the end. Some theorists propose that the Big Rip's infinite stretching could reboot the universe. Just as extreme torsion in black holes might birth new cosmos, the rip's violent expansion could create quantum fluctuations so intense they spark another Big Bang. It's a grim cycle, destruction so total it circles back to creation. The universe wouldn't just die, it would shatter like a pane of glass, with each shard potentially becoming a new reality. Whether phantom energy is real or not, it forces us to confront a profound question. Is the cosmos destined for quiet fading or violent dissolution? The answer hinges on the true nature of dark energy, a force so enigmatic it could be the universe's silent endgame or the prelude to its most dramatic reinvention. One thing's certain: if phantom energy is out there, the universe won't go gently into that good night. It'll be torn apart, screaming into the void, and in that final instant, the fabric of reality itself might just answer back. What if the universe is sitting on a knife's edge, balanced precariously above an abyss that could rewrite reality itself? This is the unsettling premise of the false vacuum theory, the idea that our cosmos might not be in its most stable state, but teetering like a boulder on a mountainside, waiting for the slightest nudge to come crashing down. Physicists call it metastable, a condition that appears solid but could collapse into something entirely different in an instant. And if Stephen Hawking was right, the consequences wouldn't just reshape the universe, they'd erase everything we know about physics, life, and existence in a sphere of destruction expanding at the speed of light. To understand this doomsday scenario, picture the universe as a vast, energy-filled landscape. Think of a ball resting in a valley. That's a stable state where it would take significant force to move it. But what if the ball isn't at the bottom of the valley? What if it's perched on a plateau with a steeper drop just beyond? That's the false vacuum, a temporary resting place where the slightest quantum fluctuation could send it tumbling into a lower energy state. In cosmic terms, this wouldn't just change the rules, it would rewrite them entirely. The speed of light, the strength of gravity, even the behavior of atoms could be altered in an instant, rendering the physics that governs our reality obsolete. Hawking famously warned that such a transition could be triggered randomly, anywhere in the universe at any moment. A single quantum event, a particle tunneling through an energy barrier, or a high-energy collision in a particle accelerator, might create a tiny bubble of this new, lower-energy vacuum. Once formed, this bubble would expand in all directions at light speed, its boundary rewriting the fabric of space as it goes. By the time you saw it coming, it would already be too late. One moment, the universe as we know it exists. The next, it's gone, replaced by a new reality with different fundamental constants. There'd be no warning, no time to react, just an invisible wall of annihilation, erasing galaxies, stars, and life itself without a trace. But why hasn't this happened yet? If the universe is metastable, shouldn't it have decayed by now? The answer lies in probability. Much like radioactive atoms, which might decay in a second or a million years, the false vacuum operates on quantum timescales. Statistically, it's possible, even likely, that the universe could remain in this precarious state for billions or even trillions of years before collapsing. Some calculations suggest the average time for such an event exceeds the current age of the universe by a factor of 10 to the power of several hundred. That's a 1 with hundreds of zeros after it, a number so large it's practically infinite for human purposes. But practically infinite isn't the same as impossible. Critics argue that the false vacuum is speculative, with no direct evidence to support it. Yet the math checks out, and the standard model of particle physics even hints that our vacuum might not be perfectly stable. Experiments at the Large Hadron Collider continue to probe the Higgs field, the energy field that gives particles mass, for signs of instability. So far, the results are inconclusive, but the mere possibility forces us to confront a humbling truth. The universe might not be the eternal, unchanging stage we imagine. It could be a temporary arrangement, a cosmic house of cards waiting for the slightest breeze to bring it all down. The most haunting part: if the false vacuum decays, the new reality it creates might be utterly inhospitable to life as we know it. The constants that allow atoms to form, stars to shine, and consciousness to emerge could vanish, replaced by a barren, alien physics where nothing recognizable exists. It's not just an end, it's a reset button for reality itself, and yet, paradoxically, this fragility might be what makes our universe so special. The very instability that threatens us could also be the reason we're here at all, a fleeting moment of balance in an endless sea of possibilities, where the laws of physics align just long enough for us to ask the question, are we living on borrowed time? Imagine waking up one day, convinced you're a real person in a real world, only to realize you're just a fleeting thought, a momentary flicker of consciousness formed entirely by chance in the vast cosmic void. This is the unsettling paradox of the Boltzmann brain, a thought experiment so bizarre it makes solipsism seem tame. The idea stems from Ludwig Boltzmann's groundbreaking work on thermodynamics in the late 19th century, where he grappled with the nature of entropy, the universe's tendency toward disorder. His equations revealed something counterintuitive. While chaos is the most probable state, statistical flukes can still create pockets of order, even something as complex as a self-aware mind, if you wait long enough. Here's the chilling part. In an infinite or near-infinite universe, the probability that random particles could assemble into a fully formed, thinking brain complete with fabricated memories of a past that never happened approaches near certainty. These Boltzmann brains wouldn't emerge from biological evolution but from sheer mathematical inevitability, like rolling a dice an infinite number of times until it lands on 1,000,000 sixes in a row. You might be one right now, hallucinating this entire reality in the split second before your disordered surroundings snuff you back into oblivion. This isn't just philosophical musing, it's a serious problem for cosmology. If the universe truly lasts forever, Boltzmann brains should statistically outnumber ordinary, evolved consciousnesses like ours by an unimaginable margin. So why do we perceive a coherent, structured universe instead of floating in chaos? Some physicists argue this paradox undermines theories of eternal inflation or cyclic cosmologies, forcing us to reconsider whether the cosmos has an endgame that prevents such aberrations. Others propose that the mere fact we observe order is evidence the universe isn't eternal, pointing to a finite timeline where Boltzmann brains haven't had time to dominate. The irony is delicious. Boltzmann's work sought to explain why we see structure in the universe, only to spawn a theory suggesting we shouldn't see any at all. It's a cosmic joke with no punchline, or worse, one we're not equipped to understand. After all, if you were a Boltzmann brain, how could you ever know? Your false memories would insist this is real, your logic would feel impeccable, and your doubt would just be part of the illusion. The theory doesn't just question reality, it obliterates the tools we'd use to question it. Yet hidden in this nightmare scenario is a strange comfort. The fact that we experience a universe that's stable, shared, and governed by consistent laws might be the best evidence that we're not Boltzmann brains after all. Unless, of course, that's exactly what such a brain would tell itself. the universe might not just be stranger than we imagine, it might be stranger than we can imagine, leaving us to wonder whether we're participants in its story or phantoms in its chaos. At the far end of time, when the universe has burned through its last stars and even black holes have evaporated into whispers of radiation, could something astonishing still be waiting? This is the radical vision of Frank Tipler's omega point theory, a hypothesis where the death of the cosmos isn't an end, but a transformation into something beyond comprehension, an infinite, all-knowing computational singularity. Tipler's idea builds on the work of physicist and theologian Pierre Teilhard de Chardin, who imagined evolution culminating in a transcendent state of consciousness he called the omega point. But where Teilhard saw metaphor, Tipler saw math. In his framework, as the universe collapses in a hypothetical big crunch, the energy density and temperature rise to unfathomable levels. Matter isn't just compressed, it's refined into an ever more efficient substrate for computation. At the point of maximum collapse, the entire cosmos becomes a single, hyper-intelligent processor, capable of performing an infinite number of calculations in the final finite moments before the singularity. How, through relativistic time dilation, as gravity grows infinitely strong near the end, time slows to a crawl from the perspective of the collapsing universe's inhabitants. Subjectively, an eternity of experience could be squeezed into those last microseconds, allowing the omega point to simulate every possible consciousness that ever could have existed. The implications are dizzying. If the universe is closed, meaning it will eventually stop expanding and collapse, Tipler argues this final state would effectively resurrect every being that ever lived, not as physical entities, but as perfectly emulated minds within the omega point's infinite computation. Your thoughts, memories, even your subjective sense of self would be recreated with flawless precision, indistinguishable from the original. In essence, the universe becomes its own afterlife, a cosmic backup where no experience is ever truly lost. Critics point out glaring holes. Modern cosmology suggests the universe is more likely to expand forever, rendering the Big Crunch scenario obsolete. Tipler counters that even in an open universe, advanced civilizations could engineer their own collapse, harnessing the energy of entire galaxies to create a local omega point. Others argue that simulating consciousness isn't the same as true resurrection, a copy of you isn't you. But Tipler's math is provocative, blending general relativity, quantum mechanics, and information theory into a grand unified vision where physics and theology collide. The omega point doesn't just challenge our view of cosmic endings, it redefines the meaning of existence itself. If consciousness is the universe's ultimate endgame, then intelligence isn't just a fluke of evolution. It's the cosmos awakening to its own destiny, a process where every thought, every choice becomes a thread woven into the fabric of reality's final act. Whether prophecy or pipe dream, the theory forces us to ask, if the universe can remember, does that make it alive? And if it's alive, what might it dream of becoming? What if reality itself is waiting for us to look before it decides what to be? That's the mind-bending premise of John Wheeler's participatory universe, a radical reimagining of existence where consciousness isn't just an observer, but an active architect of reality. Wheeler, the physicist who coined the term black hole, took quantum mechanics' strangest quirk, the observer effect, and stretched it to cosmic proportions. His it from bit philosophy suggests that the universe isn't built on matter or energy, but on information. Every particle, every force, even space-time itself, might just be answers to quantum yes or no questions, a cosmic game of 20 questions where the act of asking shapes the answers. Think of it like a cosmic choose-your-own-adventure book. In quantum experiments, particles exist in fuzzy superpositions both here and there, spinning up and down until measured. At that moment, the possibilities collapse into a single outcome. Wheeler's genius was to ask, what if this doesn't just happen in labs but everywhere, always? Imagine flipping a light switch in an abandoned house. Does the bulb burn out the moment you flip it, or was it already broken? In a participatory universe, the question itself creates the answer. Until a conscious observer checks, reality remains a tapestry of possibilities, threads waiting to be woven into history by the very act of looking. Wheeler's most famous thought experiment, the delayed choice quantum eraser, takes this even further. Picture a photon traveling through a double-slit experiment where it can behave as either a particle or a wave. Normally, measuring which slit it passes through forces it to choose particle behavior. But Wheeler realized you could wait until the photon has already passed the slits potentially as a wave before deciding whether to measure its path. Astonishingly, the photon seems to retroactively change its past behavior based on the future measurement. It's as if the universe is editing its own script in real time, with consciousness as the director shouting, "Cut," after the scene's already filmed. This isn't just philosophy. Modern physics grapples with Wheeler's legacy in theories like quantum decoherence, where observation isn't about human minds per se, but any interaction that records information in the environment. Yet Wheeler went further, suggesting the universe might have bootstrapped itself into existence through a self-referential loop. In his participatory anthropic principle, observers are inevitable because only a universe capable of producing them could ever be observed in the first place. Its reality as a cosmic art project, half finished until a viewer steps back to see the whole. Critics argue this veers into mysticism, conflating measurement with consciousness. But supporters point to quantum biology, processes like photosynthesis that harness quantum effects. As evidence, nature exploits these rules even without human observers. The debate forces us to confront a staggering possibility. The universe might not just be stranger than we imagine, but stranger than we can imagine, with our own awareness as the chisel carving reality from the quantum foam. Whether Wheeler was right or not, his vision invites us to wonder, if a tree falls in a quantum forest, does it make a sound, or any sound at all, until someone's there to hear it? The answer might rewrite not just physics, but what it means to exist. Black holes aren't just cosmic vacuum cleaners. They're the universe's strictest librarians, enforcing a rule so fundamental it might reshape our understanding of reality itself. This is the heart of Jacob Bekenstein's groundbreaking work on black hole entropy, which reveals something startling. There's a hard limit to how much information any region of space can hold. Picture trying to cram an entire library into a single bookshelf. No matter how cleverly you stack the volumes, there's a point where the shelf physically can't hold another page. Bekenstein showed that space operates the same way. The denser the information packed into a volume, whether it's the contents of a hard drive or the atoms in your body, the closer it inches toward collapsing into a black hole. This cosmic information limit suggests something radical. Spacetime itself might be pixelated, woven from tiny, indivisible bits like the pixels on a screen. Bekenstein's math builds on the holographic principle, but with a twist. When matter falls into a black hole, the information it contains doesn't vanish. It gets smeared across the event horizon in microscopic bits so fine. Each one covers an area roughly 10 billion times smaller than a proton. These aren't just random scribbles, they're perfectly ordered like the ones and zeros of a cosmic hard drive. The shocking implication, the maximum entropy, a measure of information inside any volume, isn't determined by its bulk but by its surface area. It's as if the universe is a hologram where a 2D boundary encodes everything happening in 3D space. This leads to the idea of spacetime pixels. If information has a smallest possible unit, then space and time might not be smooth and continuous but granular. Imagine zooming in on a digital photo until you see the individual pixels. At our everyday scale, reality seems seamless, but Bekenstein's work hints that if we could peer close enough, we'd find a latticework of quantum cells as fundamental as atoms are to matter. These wouldn't just be abstract math, they'd define the ultimate resolution of reality. Nothing could be smaller, faster, or more precise than these base units, putting a hard cap on the universe's processing power. The stakes couldn't be higher. If spacetime is pixelated, it challenges Einstein's vision of a smooth, flexible continuum. Sudden jumps between quantum pixels might explain strange phenomena like quantum tunneling, where particles teleport through barriers. It could even rewrite our understanding of gravity, not as a force, but as an emergent property of information flow across these microscopic tiles. Some theorists suggest that black holes are nature's way of enforcing these limits, like cosmic bouncers ensuring no region of space hogs more data than its surface area allows. Yet mysteries remain. If space is pixelated, why don't we notice? The answer lies in the scale. These hypothetical pixels would be so vanishingly small, around 1/6 × 1035 meters, that their effects only appear in extreme conditions like near black holes or in particle collisions at near light speeds. Even the most advanced particle accelerators can't probe this realm directly, but subtle clues might lurk in the cosmic microwave background or gravitational waves, where anomalies could betray the granular texture of spacetime. Wittgenstein's insight doesn't just illuminate black holes. It reframes the universe as an information processor, with every atom, every photon, every thought just data flickering across the cosmic hard drive. The pixels of reality might be invisible to us now, but if they're real, they're the brushstrokes of existence itself, painting a universe where even emptiness hums with hidden code. The universe doesn't just expand, it might be crashing into itself over and over in a cosmic demolition derby. Revisiting the ekpyrotic model, a bold twist on brain cosmology, reveals that our universe's fiery birth could have been less a singular explosion and more a head-on collision between membranes floating in higher dimensional space. Recent breakthroughs in gravitational wave astronomy are finally giving scientists the tools to test this radical idea, hunting for echoes of ancient crashes that might still ripple through the fabric of reality. At the heart of the ekpyrotic theory lies a breathtaking rethink of the Big Bang. Instead of a singularity bursting from nothing, imagine two infinite, parallel brains, sheets of reality vibrating in a vast, unseen dimension, slowly drawn together by invisible forces. When they finally collide, the energy of that impact ignites everything we know: matter, light, even time itself. It's less a creation story and more a cosmic reset, with each collision wiping the slate clean before beginning anew. Unlike traditional cyclic models relying on dark energy's ebb and flow, ekpyrosis proposes a leaner, meaner mechanism, gravity alone, warping the brains until they slam together like cymbals in a symphony of rebirth. The smoking gun for this theory might be hiding in gravitational waves, the faint tremors in space-time first detected in 2015. If the ekpyrotic model is correct, the violence of brain collisions wouldn't just produce a universe, it would send shockwaves reverberating across dimensions. Some physicists speculate these waves could carry a unique fingerprint, a telltale spectrum of frequencies distinct from those made by black hole mergers or neutron star collisions. Like finding a specific crack in a bell's chime, spotting this pattern in gravitational wave detectors could be the first direct evidence of a universe born from impact. Even more tantalizing are hints that these waves might not travel solely through our three-dimensional space. In brain cosmology, gravity is special. It's the only force not confined to our membrane, capable of leaking into the higher dimensional bulk. This means collision-generated waves could arrive in two flavors, ones trapped on our brain and others that briefly dart into the bulk before returning, creating eerie echoes in the data. Observatories like LISA, a space-based gravitational wave detector set to launch in the 2030s, might be sensitive enough to catch these ghostly duplicates, offering a glimpse into the very geometry of the higher dimensional arena where cosmic titans collide. Critics argue the ekpyrotic model has hurdles, like explaining the universe's striking uniformity without invoking inflation's rapid stretching. Yet proponents counter that brane collisions naturally flatten and smooth the cosmos, like rolling out wrinkles in a carpet with a single decisive pull. Others question whether gravitational waves from such ancient events could persist, but if space-time carries even a trace of memory, like a tuning fork humming long after it's struck, the right tools might yet hear their song. The implications are staggering. If ekpyrosis is real, our universe isn't just one chapter in an endless cycle. It's a single frame in an infinite cosmic film strip, each collision a reset button pressed by gravity's inexorable hand. And somewhere out there, in dimensions we can't see or touch, the next impact might already be brewing, set to ignite a universe we'll never know, one that could, in turn, ask the same questions about us. What if the quantum world's chaos isn't chaos at all, just a veil hiding a deeper, invisible harmony? This was physicist David Bohm's radical vision, one that dared to rewrite quantum mechanics' most baffling rulebook. While mainstream science embraced probabilities and uncertainty, Bohm saw ripples on the surface of something far deeper, an implicate order, a hidden architecture where every electron's spin, every photon's path, is guided by unseen forces woven into the fabric of reality itself. Imagine watching a whirlpool in a river. The water's surface dances with apparent randomness, but beneath lies a structured current, invisible yet undeniably real. Bohm argued quantum particles behave the same way, their seemingly erratic choices steered by mysterious, hidden variables operating beneath spacetime's stage. Bohm's theory emerged from his frustration with the Copenhagen interpretation, which famously declares particles don't have definite properties until measured. Instead, he proposed that quantum weirdness-like entanglement, where particles instantly influence each other across vast distances, isn't spooky action at all. It's the natural outcome of an unbroken wholeness, a cosmic tapestry where separateness is an illusion. Picture two dancers on opposite sides of a stage, moving in perfect sync, not because they're signaling, but because their steps are choreographed by the same submerged rhythm. In Bohm's universe, every particle is connected to every other through this hidden dance, with the implicate order as the silent conductor. The math behind this is both elegant and daunting. Bohm's pilot wave theory reintroduces determinism to quantum mechanics, suggesting particles have real trajectories even when unobserved. These paths aren't random, they're sculpted by a quantum potential, a field carrying information about the entire experimental setup. It's as if an electron passing through a double slit knows whether the other slit is open not through magic, but because the quantum potential, a kind of cosmic GPS, guides it based on the whole environment. This potential doesn't push or pull like gravity. It subtly informs, like a whispered suggestion shaping a dancer's next move. Critics dismissed Bohm's ideas as inelegant, adding unnecessary complexity to quantum theory. After all, hidden variables can't be measured directly, and the math produces the same predictions as standard quantum mechanics. But supporters counter that Bohm's framework eliminates quantum paradoxes without invoking multiple worlds or collapsing wave functions. It also offers something rare in modern physics, a visualizable reality where particles are more than probability clouds. Recent experiments with oil droplets bouncing on vibrating surfaces, uncannily mimicking quantum behavior, have breathed new life into pilot wave theory, hinting that Bohm's hidden order might not be so hidden after all. The implicate order doesn't just challenge physics, it reshapes how we see existence. If Bohm was right, the universe isn't a collection of isolated objects, but a flowing, holographic whole where every part contains the whole. Even your act of reading these words might ripple through the quantum potential, a whisper in the cosmic symphony. The question isn't just whether Bohm's vision is true, but what it would mean if it were. Would randomness itself be an illusion? Could consciousness play a role in navigating this hidden architecture? the answers might lie not in smashing particles, but in learning to see the universe as Bohm did, not as fragments, but as an unbroken dance. What if everything in the universe, every star, every planet, every atom ultimately adds up to nothing? That's the startling promise of the zero-energy universe theory, which suggests the cosmos might be the ultimate free lunch. At first glance, the idea seems absurd. After all, the universe contains an unimaginable amount of matter and energy, enough to fuel billions of galaxies for billions of years. But dig deeper, and the math reveals a cosmic balancing act so precise it borders on poetry. The key lies in gravity's hidden ledger. While matter and energy contribute positive values to the universe's balance sheet, gravity, the force that sculpts galaxies and bends spacetime, carries negative energy. Think of it like digging a hole in the ground. The pile of dirt represents positive energy, while the hole itself embodies negative energy. Combine them and you're left with flat ground, zero net change. Similarly, the universe's total positive energy from matter might be perfectly offset by gravity's negative energy, leaving the cosmic books balanced at zero. This radical idea traces back to physicist Richard Feynman's insight that a falling object's gravitational potential energy is negative, cancelling out the kinetic energy it gains during the fall. Extrapolate this to the entire cosmos, and you get Alan Gough's inflation theory, where the explosive expansion of the early universe could have borrowed energy from gravity's negative balance, producing a vast, structured cosmos without requiring any initial energy input. It's as if the universe took out a loan from itself, using gravity's negative pull as collateral, a self-funding creation where the debt never comes due. The implications are staggering. If true, the Big Bang wasn't an explosion of energy from nothing. It was a quantum fluctuation in a zero-energy system where positive and negative terms cancelled out. Even now, every particle of matter might be paired with a corresponding hole in spacetime's curvature, like shadow twins keeping the cosmic scales even. This could explain why the universe seems so finely tuned for complexity. Any imbalance would have caused immediate collapse or runaway expansion, leaving no room for galaxies or thinkers to emerge. Critics argue that defining gravity's energy is notoriously tricky in general relativity, with some formulations rejecting the concept altogether. Yet supporters point to black holes, where the energy required to tear spacetime matches the negative gravitational energy of the singularity, as evidence the math holds in extreme conditions. Others suggest the zero-energy hypothesis resolves the mystery of why the universe's total mass-energy density is so eerily close to the critical value needed for flat geometry. It's not a coincidence, but a necessity baked into existence itself. The zero-energy universe doesn't just challenge our notions of creation, it redefines nothingness. If the cosmos truly balances to zero, then reality might be less a thing that exists and more a fluctuation that persists, a temporary ripple in the infinite quiet. Far from diminishing our significance, this view makes existence all the more miraculous, a self-balancing act of physics where something as vast as a universe can emerge from nothing at all, and where every atom is a stroke of cosmic accounting so perfect it borders on art. What if spacetime isn't the smooth, flowing fabric Einstein imagined, but a vast, invisible crystal, a lattice of unimaginably tiny pixels frozen in a cosmic grid? This is the essence of the crystalline universe hypothesis, a radical rethinking of reality's deepest layer. At scales trillions of times smaller than an atom, the theory proposes that space and time aren't continuous but stutter forward in discrete steps like frames in an old film reel. The implications shake the foundations of physics. If space-time has structure, then the universe might not just exist within dimensions, it might be built from them block by block. The idea stems from attempts to reconcile general relativity with quantum mechanics. Einstein's equations treat spacetime as pliable and seamless, bending like rubber under gravity's touch. Yet quantum theory insists everything energy, momentum, even properties like spin, comes in indivisible packets. The clash creates paradoxes like black holes where infinite density meets quantum uncertainty. To resolve this, physicists like Carlo Rovelli and Lee Smolin suggest spacetime itself must be quantized at the Planck scale, distances so small, around 10 to the power of minus 35 meters, that measuring them would require so much energy it would collapse into a black hole. In this realm, the smooth geometry we know shatters into a shimmering network of interconnected nodes, more like a cosmic circuit board than empty void. Evidence for this crystalline structure might be hiding in plain sight. Just as light passing through a prism splits into colors, high-energy gamma rays traversing quantized spacetime should scatter slightly depending on their wavelength, an effect some telescopes may have already glimpsed. In 2009, observations of distant gamma-ray bursts revealed photons of different energies arriving at Earth microseconds apart, as if space itself had a texture that slowed some more than others. Critics argue these delays could stem from magnetic fields or interstellar dust, but supporters counter that the pattern matches predictions of certain spacetime lattice models. Even more tantalizing, if spacetime is granular, it could explain why the speed of light is constant. Photons might be hopping between lattice points at a fixed maximum rate, like data packets traveling through fiber optic cables. The crystalline universe doesn't just challenge how we see space, it redefines time. In this framework, the present isn't an infinitesimal slice between past and future. It's a Planck-sized chronon, a quantum of time lasting roughly 10 to the power of minus 43 seconds. Between these moments, time might not flow at all, rendering motion an illusion stitched together by our macroscopic perception. Think of a flipbook where each page is static, yet flipping creates the illusion of movement. Our conscious experience could be the cosmic equivalent, with reality updating in quantum snapshots too rapid for any instrument or mind to detect individually. What does this mean for black holes, wormholes, or the Big Bang? If spacetime is pixelated, singularities might not be infinitely dense points, but the final pixel at the bottom of the cosmic zoom. Wormholes could emerge as shortcuts between lattice nodes, like secret corridors in a dungeon's grid. Even the universe's expansion might look different, not smooth stretching, but the gradual addition of new spacetime cells, like a 3D printer assembling reality layer by layer. The crystalline model offers something rare in theoretical physics, a tangible, almost architectural vision of the void. Emptiness isn't empty, it's a bustling construction site where the universe constantly lays new foundations. Yet mysteries linger. If spacetime is discrete, what generates the lattice? Some theories invoke spin networks, abstract webs where each intersection carries quantum information about volume and geometry. Others imagine a dynamic foam with Planck-scale bubbles continuously forming and dissolving. The most radical proposals suggest the lattice itself is sentient, a self-organizing system where spacetime learns and evolves. While these ideas push the boundaries of testability, they underscore a profound shift in cosmology. The universe may not just have laws, it may have a skeleton, a hidden architecture waiting to be mapped. And if we ever decode its blueprint, we might find that reality isn't a stage we move through, but a structure we're woven into, thread by quantum thread. The holographic principle shook our understanding of reality by suggesting the universe might be a two-dimensional projection. But what if this cosmic illusion holds the key to one of physics' greatest mysteries? Enter holographic dark energy, a theory weaving together two seemingly unrelated puzzles: the holographic bound on information and the universe's accelerating expansion. Imagine the cosmos as a sphere with us at its center, its surface crammed with microscopic bits encoding everything inside. Now picture those bits not just storing reality, but actively pushing its boundaries outward like a balloon inflating because the characters drawn on its skin demand more space. This bold idea reimagines dark energy, the mysterious force accelerating the universe's expansion, not as some exotic fluid filling space, but as a consequence of information limits at the cosmic horizon. The math traces back to physicist Raphael Bousso's work on holographic bounds, showing the maximum entropy or information any region can contain depends not on its volume but its surface area. Apply this to the observable universe and something startling emerges. The energy density required to maintain this bound aligns eerily with measured values of dark energy. It's as if the universe is expanding because the holographic hard drive at its edges is hitting storage capacity, forcing spacetime to stretch to accommodate new data. Critics initially dismissed this as numerology, a coincidence of numbers without physical mechanism, but the theory gained teeth when researchers realized quantum fluctuations at the horizon could generate repulsive pressure. Picture the universe's edge as a buzzing hive of virtual particles popping in and out of existence. Normally, these fluctuations cancel out, but in a holographic framework, their energy could collectively push against the horizon like crowd surfers at a concert, driving expansion from the perimeter inward. This wouldn't just explain dark energy's strength, it'd account for why its density remains constant as space grows, a feat traditional models struggle with. The most tantalizing clue: holographic dark energy naturally predicts an equation of state, the ratio of pressure to density, slightly different from the standard cosmological constant. Current telescope data hints this might be true, with dark energy's behavior deviating from Einstein's lambda by about 5%. Future missions like ESA's Euclid telescope could measure this discrepancy with precision, potentially confirming whether the universe's acceleration is really a side effect of cosmic information processing. Yet the implications run deeper than cosmology. If holographic dark energy is real, it suggests the universe isn't just governed by laws of physics, it's constrained by information theory. The same principles limiting your laptop's memory might dictate how galaxies fly apart. Space isn't merely expanding, it's recalculating, adapting its geometry to preserve the holographic rule that surface area, not volume, holds the ultimate ledger of reality. In this view, dark energy isn't a thing at all. It's the universe's way of keeping its books balanced, ensuring no region ever contains more information than its boundaries can encode. The cosmos isn't just stranger than we imagined. It might be running on rules we've only begun to decipher, written not in forces or particles, but in bits and boundaries. What if every particle in our universe has a cosmic doppelganger, a mirror image made of antimatter, moving backward through time? This isn't science fiction. It's a serious prediction of CPT symmetry, one of the most ironclad rules in physics. The idea hinges on three fundamental symmetries: charge C, where particles swap their electrical polarities; parity P, flipping their spatial orientations like a mirror reflection; and time T, reversing the arrow of their motion. Individually, these symmetries get violated, like in certain radioactive decays where nature favors one direction over its mirror image, but combine all three and something remarkable happens. CPT symmetry insists the universe must look identical if you simultaneously flip every particle's charge, mirror its position, and run the clock backward. This leads to a staggering implication. If CPT holds absolutely, there should exist an antimatter counterpart to our cosmos, a mirror universe where positrons take the place of electrons, quarks spin in reverse, and time flows from Big Bang to what we'd consider the past. Not just a parallel reality, but an inverse one, threaded through our own like a photographic negative superimposed on the original. Imagine two movies projected on the same screen, one running forward, the other backward, each frame perfectly matched yet opposite. That's the CPT mirror universe, a cosmos born from the same singularity as ours, but unfolding in reverse. Its galaxies made of anti-stars and anti-planets. Its history a rewound version of our own. The wildest part, this mirror realm might not be entirely hypothetical. Neutrinos, those ghostly particles that barely interact with matter, could be the key to detecting it. Certain neutrino oscillations, flips between flavors like electron, muon, and tau, appear to violate CP symmetry, hinting they might also break T symmetry when examined closely. If so, these particles could be cosmic ambassadors straddling both universes, experiments like Ice Cube and Super Kamiok, and are hunting for sterile neutrinos, hypothetical particles that might interact only with gravity, slipping between our universe and its CPT mirror like shadows passing through a wall. Critics argue that a full CPT mirror universe requires conditions beyond current physics, like negative energy densities or exotic quantum states. Yet supporters point to anomalies in cosmic ray data where high-energy particles seem to arrive from directions that shouldn't be possible, as potential fingerprints of collisions with this anti-world's matter. Others suggest the universe's missing antimatter, a long-standing mystery, might be hiding in plain sight as the mirror cosmos, forever out of sync with our timeline. The implications are mind-bending. If the mirror universe exists, it could redefine entropy, causality, even the nature of time itself. Entropy might always increase in both directions from the Big Bang, like a double-ended arrow of time. Events we perceive as cause and effect could have mirror counterparts where effects precede causes. And somewhere out there, you might be living your life in reverse, with every decision you make here echoing there as an unraveled choice. Whether physics' ultimate symmetry holds the key to a hidden twin universe, or remains a beautiful mathematical abstraction, CPT forces us to confront a profound truth. Reality might be far stranger and far more balanced than we ever dreamed. Why does the quantum world's weirdness, where particles exist in multiple states at once, collapse into the familiar, solid reality we see around us? The answer might lie not in some mysterious observer, but in a relentless cosmic competition Wojcicka calls quantum Darwinism. Picture a forest where only the hardiest trees survive. In this theory, quantum states don't vanish because we look at them. They're selected by their environment, with the most robust configurations outlasting the fragile ones. At the heart of this idea is decoherence, the process where quantum systems lose their fuzzy superpositions by interacting with their surroundings. When an electron passes through a double slit, it's not just the act of measurement that forces it to choose a path. It's the relentless bombardment by photons, air molecules, and even cosmic rays that shreds its quantum coherence like a document fed through a shredder. Dirk's genius was to realize this isn't random destruction. It's nature's way of filtering reality, promoting states that can withstand environmental scrutiny while discarding those too delicate to persist. These surviving states become the classical world we perceive, not because they're special, but because they're the ones durable enough to leave copies of themselves everywhere, like footprints in wet cement. Quantum Darwinism takes this further by asking, how do certain quantum states manage to imprint their information on the environment so effectively? Imagine tossing a rock into a pond. The ripples don't just vanish, they spread, carrying the rock's impact to every corner of the water's surface. Similarly, the quantum states we perceive as real are the ones whose information gets redundantly copied into the environment, making them accessible to multiple observers. A table isn't solid because it's inherently classical, it's because countless photons bouncing off it have broadcast its position and shape to the universe, creating consensus. This framework solves one of quantum mechanics' biggest headaches, the measurement problem. Instead of relying on vague notions of observers collapsing wave functions, quantum Darwinism suggests objectivity emerges naturally. The states we all agree on, like the moon being in the sky even when no one looks, are simply the ones that have infected the environment with their information most thoroughly. It's not that the moon's position is magically fixed. It's that its quantum state has been copied so many times by stray photons and dust particles that any alternative becomes statistically insignificant. Experimental support is mounting. In labs, physicists have watched as quantum systems interacting with their surroundings rapidly shed fragile superpositions, leaving behind only the robust, classical-looking states. One experiment even mimicked natural selection by subjecting quantum bits to artificial environments. The states that survived weren't the most interesting, but the ones best at replicating their information, like a virus thriving in a host. The implications ripple far beyond physics. If quantum Darwinism holds, reality isn't a passive stage, it's an arena where information fights for survival, and what we perceive is just the winning faction. Consciousness isn't necessary to collapse the quantum world. The environment does the heavy lifting, with our observations merely tapping into a consensus forged by countless interactions. It's a humbling reminder that the solidity of our world might just be the echo of quantum states loud enough to be heard above the noise of existence, a cosmic game of last one standing where only the noisiest survive. What if gravity isn't a fundamental force at all, just a side effect of the universe's relentless slide into chaos? This is the radical premise of Eric Verland's entropic gravity, a theory that reimagines Newton's apple and Einstein's curved spacetime as illusions spun from the deeper laws of thermodynamics. Forget masses pulling on each other across empty space. In Verland's universe, gravity emerges from the microscopic shuffling of information, like the way heat flows not because it wants to, but because nature craves disorder. The idea builds on physicist Jacob Bekenstein's revelation that black holes possess entropy, a measure of disorder tied to the information smeared across their event horizons. Verland took this further, proposing that all gravity arises from entropy, gradients, differences in the amount of hidden information in space. Picture a crowded room where people naturally shift toward emptier areas to maximize their freedom of movement. Similarly, matter might fall toward regions where entropy can increase most efficiently, creating the illusion of gravitational attraction. It's not that Earth pulls the moon moves to maximize the universe's overall disorder, like a die rolling to its most probable face. This isn't just philosophical wordplay. Verland's math reproduces Newton's inverse square law and even Einstein's general relativity without invoking gravity as a fundamental force. Instead, he treats spacetime as a holographic memory system where particles interact by modifying the entropy of surrounding space. When an object moves, it effectively updates the cosmic hard drive, and gravity emerges as a statistical tendency, like how pressure in a gas isn't a force itself, but the average effect of countless molecular collisions. The most startling prediction: entropic gravity might explain dark matter without invoking invisible particles. Galaxies rotate faster than visible matter alone should allow, but Verland's framework suggests this extra pull comes from entropy differences in the universe's underlying information field. It's as if the cosmos has a built-in accounting system where gravity's extra strength in galaxies reflects hidden thermodynamic work being done at the quantum level. Some astronomers even claim certain galactic motions match Verland's predictions better than traditional dark matter models, though the debate remains fiercely unresolved. Critics argue entropic gravity struggles to explain phenomena like gravitational waves or the precise orbits of binary pulsars. Yet supporters counter that the theory is still young, much like quantum mechanics in the 1920s, and that its potential to unify gravity with thermodynamics is too compelling to dismiss. Experiments are underway to test its predictions, like measuring tiny entropy changes in controlled quantum systems subjected to gravity. Verland's vision doesn't just demote gravity, it elevates information to the cosmos's foundational currency. If he's right, the force that binds planets and bends light isn't a brute interaction, but a subtle negotiation between order and chaos, played out on the universe's deepest ledger. The next time you drop your phone, remember, it's not falling. The universe is just editing its memory one entropic step at a time. Black holes famously trap everything inside them, but what if our entire universe is the explosive aftermath of a black hole's polar opposite? White holes, long dismissed as mathematical curiosities, are making a dramatic comeback in cosmology. Unlike their dark counterparts, white holes can't be entered, only exited. Matter and energy erupt from them like water from a cosmic fire hose, blasting outward with irresistible force. Now, bold theorists are asking, could the Big Bang itself have been the universe's most spectacular white hole eruption? The math behind this idea is surprisingly elegant. When physicists run Einstein's equations for black holes backward in time, they get white holes regions where space-time flips inside out, transforming an endless pit into an inexhaustible fountain. Russian cosmologist Igor Novikov first proposed in the 1960s that our expanding universe might resemble the aftermath of such an event. Recent simulations show that quantum corrections near a black hole's core could trigger a bounce, reversing collapse into explosion. Picture a collapsing star hitting a quantum speed bump instead of crushing into a singularity. It rebounds as a white hole, birthing a new spacetime in its wake. Evidence might be hiding in plain sight. Stephen Hawking calculated that evaporating black holes should emit radiation with subtle imprints of swallowed information. If the Big Bang was a white hole, its counterpart radiation, dubbed Hawking points, could linger as faint circular patterns in the cosmic microwave background. Astronomers have already spotted several anomalous hot and cold spots in the CMB with concentric rings around them, like ripples from a pebble dropped in a pond. While mainstream cosmology attributes these to random fluctuations, white hole proponents argue their distribution matches predictions for a bounced universe's fingerprint. The theory's most provocative implication: time might not end at a white hole's birth, it could begin there. Unlike black holes, which warp future events toward a singular fate, white holes represent absolute beginnings where causality itself is rebooted. This neatly sidesteps the Big Bang's thorniest problem, the need for a before. In white hole cosmology, the question is meaningless, just as asking what's north of the North Pole. The Big Bang wasn't an eruption from nothing. It was the first tick of a new clock, the moment when a previous universe's collapse reversed course in a fiery rebirth. Critics highlight major hurdles. White holes are notoriously unstable in classical physics, prone to collapsing into black holes if any external matter falls in. Yet quantum gravity models suggest their instability might be an illusion. What looks like collapse from the outside could be a seamless transition into a new spacetime geometry from within. Others argue that without a mechanism to explain how a parent universe's information transfers to its white hole offspring, the theory remains speculative. The most tantalizing possibility: if white hole cosmology is correct, other universes might have left detectable, umbilical scars in our cosmic background. Future gravitational wave detectors could hunt for faint echoes of pre-Big Bang events, not as vibrations in space, but as wrinkles in time itself. Whether the theory holds up or not, it forces us to confront a breathtaking alternative. The cosmos might not have started with a bang, but with a bounce, a defiant reversal of cosmic destiny that turned destruction into creation and oblivion into everything we know. What if the universe isn't just governed by physics? It is physics constantly rewriting its own rules like a self-improving AI. This is the electrifying premise of Vitaly Vanchorin's neural network hypothesis, where space-time isn't a static stage but a dynamic learning system, evolving through cosmic trial and error. Picture the cosmos as a vast, self-adjusting algorithm, each galaxy, each particle, acting like a neuron in a celestial brain, firing signals across the fabric of reality itself. Vanchorin's theory starts with a startling observation. The equations describing how neural networks learn bear an uncanny resemblance to those governing quantum mechanics. In machine learning, networks adjust their connections through backpropagation, fine-tuning weights to minimize errors. Similarly, quantum systems seem to explore countless paths before settling on the one that minimizes action, a principle called the path integral formulation. The parallel isn't just poetic, it's mathematical. Van Choren suggests this isn't coincidence but evidence of a deeper unity. The universe might literally be a neural net where physical laws emerge from information processing, not the other way around. Take gravity, for example. In this framework, Einstein's curvature of spacetime could be an emergent property, not a fundamental force, but the net effect of trillions of microscopic adjustments in the cosmic network. Imagine training a deep learning model to predict the motion of planets. Over time, it invents an invisible field, gravity, to explain the patterns. Now scale that up. If the universe is the ultimate learning machine, its training data might be the quantum fluctuations of the early cosmos, and general relativity could be its best fit algorithm. The implications spiral outward. Quantum entanglement, where particles instantly influence each other across vast distances, might just be hidden layers in the network connections that bypass our intuitive sense of space. Even the arrow of time could reflect the universe's learning trajectory, with entropy as the cosmic error function it's constantly trying to minimize. Van Choren's most provocative suggestion: the reason we can't find a unified theory of physics isn't because we're missing a piece, it's because the rules themselves are still evolving, honed by 13.8 billion years of cosmic experience. Critics argue this conflates metaphor with mechanism. Just because two systems share math doesn't mean they're the same. Yet supporters counter that neural networks are universal approximators capable of mimicking any function given enough complexity. If the cosmos is fundamentally a computational process, why wouldn't it resemble the most efficient learning structures we've discovered? Some even speculate that dark energy, the mysterious force accelerating expansion, could be the universe's equivalent of overfitting, where its training pushes it toward states we perceive as runaway growth. The most tantalizing question isn't whether the universe is a neural net, but what it's learning. Is it optimizing for stability, complexity, or something beyond our comprehension? Could galactic superstructures be synaptic weights in a computation whose purpose we're too small to see? For now, these questions hover at the edge of science, but the mere possibility reshapes how we view existence. Reality might not be a fixed set of rules, it could be a living equation, rewriting itself in real time, with every particle interaction a step toward cosmic mastery. What if the universe isn't just an expanding sea of matter and energy, but a vast ticking clock, its gears forged from the fabric of reality itself? This is the breathtaking vision of time crystals, a revolutionary phase of matter first theorized by Nobel laureate Frank Wilczek in 2012. Forget diamonds or ice, these crystals don't exist in space alone, but in time itself, their atomic structures oscillating in perfect, perpetual motion without energy input, like a cosmic pendulum that never winds down. Time crystals defy everything we thought we knew about equilibrium. Normal matter settles into its lowest energy state, like a ball rolling to rest at the bottom of a hill. But time crystals are nature's paradox. They're stable yet never static, cycling through states with clockwork regularity, even at absolute zero, where all motion should cease. Imagine a diamond where the carbon atoms not only form a lattice but also rotate in sync, flipping their orientations like a chorus line whose routine repeats indefinitely without dancers ever tiring. That's the essence of a time crystal, not just structure in space, but structure in time, a rhythm woven into the quantum fabric of existence. Wilczek's inspiration came from a deceptively simple question: could matter exhibit crystalline order in the fourth dimension, just as it does in the three spatial ones? The math said yes, but the implications upended centuries of physics. Time crystals don't violate thermodynamics, they don't create energy, but they dance around its edges, sustaining motion without energy loss. Picture a frictionless metronome ticking forever in the void, its beats marking not just musical time but the hidden pulse of the universe. The real magic lies in how they form. Unlike regular crystals, which emerge when atoms freeze into orderly patterns, time crystals arise from quantum entanglement, the eerie link between particles that Einstein called spooky action at a distance. When entangled particles are nudged by a laser or magnetic field, they don't just respond once. They enter a loop of synchronized flips, their collective rhythm resistant to disturbances. This isn't just theoretical. In 2017, two teams, one at Harvard, another at the University of Maryland, built the first time crystals using chains of ytterbium atoms and diamond defects, proving Wilczek's vision wasn't just elegant math but a new state of matter. Now, the wildest question: could spacetime itself be a time crystal? Some theorists suggest the universe's expansion might carry subtle periodicities, like a heartbeat echoing across billions of years. Others propose that dark matter could consist of time crystalline structures, their invisible oscillations shaping galactic rotation curves. Even the arrow of time might find roots here. If the cosmos has an inherent rhythm, it could explain why we remember the past but not the future, like a needle moving only one way on a cosmic record. Time crystals don't just challenge our understanding of matter, they hint that the universe might be more dynamic, more musical than we ever imagined. Reality isn't just a static stage, it could be a symphony of self-sustaining vibrations, each atom keeping time in a dance that began at the Big Bang and will never ever stop. From holographic projections to cosmic neural networks, from white hole bangs to self-adjusting spacetime, the sheer audacity of these theories proves one thing: the universe isn't just stranger than we imagine, it's stranger than we can imagine. Each of these ideas isn't just a flight of fancy, it's a calculated leap at the edge of human understanding, where mathematics and madness dance on the razor's edge of possibility. Whether it's black holes birthing new realities or the universe learning its own rules as it unfolds, these aren't just answers, they're invitations to ask even wilder questions. What's truly remarkable is how these theories refuse to settle. They don't just challenge the status quo, they set it on fire. A century ago, the idea of parallel universes or time crystals would have been dismissed as fantasy. Today, they're serious science, debated in lecture halls and tested in quantum labs. That's the beauty of cosmology. Every answer unravels 10 new mysteries, and every limit we think we've hit is just another frontier waiting to be crossed. So, which theory shattered your reality? Was it the Boltzmann brain nightmare, the thought that you might be a fleeting accident in the void, or the holographic principle, turning everything you know into a cosmic mirage? Maybe it was the neural network universe quietly rewriting its own laws like some kind of alien AI. Drop your mind-blown reactions in the comments. We're all just cosmic detectives here, piecing together the greatest mystery of all. If your brain's still buzzing from these ideas, you're not alone. The universe's secrets don't stop here, and neither do we. Hit subscribe to keep diving deeper into the unknown, because one thing's certain: the next revelation is already out there, lurking in the math, waiting to turn everything we think we know inside out. The cosmos isn't done surprising us, and neither are